So the poorly stabilized charge on carbon enables both alkyl lithium and Grignard reagents to behave both as strong bases and strong nucleophiles. Okay. So for example, both the alkyl lithium reagent, which is shown right here, and the Grignard reagent, which is shown right here, react rapidly with water in really exothermic proton transfer reactions, both shown here and here. And they produce an alkane and a base, that OH minus. And these products are much more stable because the negative charge is transferred from, say, a carbon atom to a more electronegative oxygen. So these guys, both the alkyl lithium reagents and Grignard reagents, are very reactive in their own right. And so a lot of times we don't want to just get an alkane from them. And so they need to be kept away from any sort of water source to make sure that they're not kind of deactivated by the presence of water. Now, remember from chapter 7 that we usually treat organometallic compounds like Grignard reagents or alkyl lithium reagents as just straight up alkyl anions. So if you see this, because there's such a difference in electronegativity, you can go ahead and shorten it to just there being an anion wherever the lithium was bonded to, or an anion wherever the magnesium was bonded to. So we can simplify these reagents. Now, even though we can simplify these and say these organometallic reagents react as if they're just R minus, they're truly not really ionic. When they're dissolved in solution, the free R minus doesn't exist. Instead, think of them as R minus donors. And kind of in that same way that we view lithium aluminum hydride and sodium borohydride as H minus donors. This is an example of a reaction, and this is how we would show that reaction as kind of this R minus donor. We would start the arrow here in between the carbon and the lithium, and these electrons go here, and those electrons go there. And so the lithium is replaced by the proton, in this case, in a proton transfer reaction. Now, even though alkyl lithium and Grignard reagents are strong bases, they don't deprotonate an alpha carbon of a polar pi bond. Instead, the R minus acts as a nucleophile. And so when R minus acts as a nucleophile, what we see then is, and we can see this through the mechanism, is it's going to attack. And so I'm going to draw this, I'm going to draw the simplified version, and you're more than welcome to as well. So all I've done is I've taken what's here in red, and I've said, okay, hey, look, I'm gonna cut that lithium off, right? And it's CH3, CH2, CH2, CH2. There are 3 CH2s there, and I'm going to redraw it this way. And so I'm going to say, okay, hey, look, those electrons are going to come here and attack this partially positive carbonyl carbon. And these electrons are then going to go up on the oxygen. Now, when that occurs, that's a nucleophilic addition. And so now, if we follow our arrows, we can see there's an O minus there, but at the same carbon, now we have an alkyl group. One, two, so I felt like I was missing carbon there. So we've got 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. Okay, so I've got the same number of carbons. I want you to notice here that this is a way to attach an alkyl group to the carbonyl carbon. And so we can also change the length of the carbon chain by using this reaction. Now, this second thing right here, this is an acid workup. And so we can simplify this to say we have OH3 plus, okay? And so what's gonna happen are these electrons are gonna come steal that proton. Those electrons are gonna go there. This is a proton transfer reaction. And now we have an alcohol. With 1, 2, 3, 4 carbons there. So this, that R minus acts as a nucleophile, and it's attracted to the partial positive charge of the carbonyl carbon. We can also see reactions similar to this with nitriles, for example. So let's look at this reaction. This is a Grignard reagent. So when we look at the mechanism for this particular reaction, I know that because this is a Grignard, I can shorten it and put the negative charge kind of here where I've drawn the line. And so I can say, okay, hey, look, it's completely symmetric, so just pick a carbon. It doesn't matter which one. And then I know that this nitrogen's really electronegative. That makes this carbon electropositive, so it's an electrophile. Now my Grignard is a nucleophile. Those electrons are going to go here, and again we're going to have nucleophilic addition where those electrons go there. Now I am going to follow my arrows, and I start with the things that don't change. That first ring doesn't change, right? I'm attached to a carbon, and then on the other side now we've got some changes. I've got another ring here, and then this nitrogen is going to have a double bond, and now it's going to have 2 sets of electrons and negative charge. And so we can again do an acid workup, which is shown here with number 2, right, where we're going to have our alcohol that's going to act like a weak acid. And so what happens, and I didn't leave, I don't love how I did that, so I'm going to erase it. Wanted to leave space there. So what's going to happen is that these electrons are going to come steal that proton. Those electrons are going to go on the oxygen. And now what we see right, is that molecule. So again, nucleophilic addition and then proton transfer. So we see, you should be able to see the similarities between the Grignard reagents and the alkyl lithium reagents. Now, we want to look at one more Grignard reaction really quick that's kind of important, and it's this one here. What we see is that we have a Grignard reagent that reacts with carbon dioxide. Now, carbon dioxide is a nonpolar compound overall. So remember, it looks like this, where we've got 2 kind of polarities, like one pulling this way and one pulling that way. So it's really polar. These cancel each other out. But this bond right here is polar, and this bond right here is polar. So this is an example of a molecule that's nonpolar overall, but has 2 polar bonds. Now, because of that, this central carbon is really quite electron poor, right? It's going to have a partial positive because both of these are electronegative. And so that can be susceptible to a nucleophilic attack. So Grignard reagents can add to CO2 in what's called a carboxylation reaction, and we form a new carbon-carbon bond. Now notice CO2 is shown in blue here, and we're going to form CO2 right here like this, where the Grignard has attacked the Grignard here has attacked the carbonyl carbon. These electrons have been bumped up here, and then it steals a proton from an acid workup, right? In the very same way that we've seen before. Now, there's some drawbacks to alkyl lithium and Grignard reagents, and one of those is we do have some functional groups that are incompatible with alkyl lithium and Grignard reagents. These are shown here. To carry out a desired nucleophilic addition with a Grignard or a alkyl lithium, add a particular carbonyl or carbon double bonded nitrogen or carbon triple bonded nitrogen bond, any of those, you need to avoid incompatible groups, okay? So carbon double bonded to oxygen, carbon double bonded to nitrogen, and carbon triple bonded to nitrogen groups elsewhere that would undergo a nucleophilic addition, okay? So if this is the desired reaction, this is an incompatible group because this can also react over there, okay? Same thing here. If this is the desired reaction, this is an incompatible group because this can also react with that. Acidic groups like OH here, right, and NH will undergo deprotonation, right? And so that would be an incompatible group because even though you're desiring this reaction, there'd be a deprotonation reaction that would happen instead, right? Alkyl halides can undergo, which were shown here, which I mentioned before, can undergo E2 elimination reactions with Grignards. And then epoxides can undergo ring opening reactions. So we do have to be kind of careful because Grignards are very reactive to when you're setting up a reaction, when you're doing a synthesis, to make sure there aren't any other compatible, in what we call incompatible groups. But really what we're saying is other groups that can react and have synthetic traps, okay? So that's just something to watch out for as we become more complex in what we learn about what Grignards and alkyl halides can do. Oh, sorry, alkyl lithium reactions can do.